Hi everyone, Charles here for MLU Papers. On October the 9th, 2024, David Baker, Demis and John Jumper officially became the recipients of the Nobel Prize in Chemistry 2024 for their foundational work on protein predictions and design, notably with the algorithm AlphaFold 2. Now, why did they get the Nobel Prize? And what is their work about? Let's find out. A long-standing problem in biochemistry. First, let's start with some background on proteins. Proteins are at the core of life and underlie so many of our vital functions. The hemoglobin that stores oxygen in our red blood cells, that's a protein. The antibodies that protect us against viruses, they're proteins. The insulin hormone that regulates our blood sugar level, a protein. Our muscles, 80% proteins. Our skin, nails, bones, organs, mostly proteins too. Proteins are everywhere and can be of any length and shape. And their understanding literally saves lives. That's how antibiotics work. The penicillin, for instance, works by inhibiting the bacterial protein which synthesizes cell walls, making them vulnerable to our antibodies. However, a bacteria which survives after a prolonged contact with the antibiotics would in turn evolve and learn how to produce a molecule that breaks down penicillin. That's like a protein war, and by the way, that's one reason why one should always respect a doctor's antibiotics prescription. In particular, you should never ever decrease the dosage or the duration of a treatment, even if you feel better, or you might allow the proliferation of ultra-resistant bacteria both inside and outside your body. And as you can see, proteins are central in that story. But what is a protein exactly? Structurally, a protein is a sequence of many amino acids, and by many, I mean from 50 to several thousands. In the human body, each of those amino acids can be one of those 21 different types. Since 1961, we know that the types of amino acids that compose a protein entirely determine its shape. At that time, one of the main ways to determine the shape of a protein was X-ray crystallography, which works in two steps. First, we grow a crystal of our protein. That is a nice and regular arrangement of many copies of our protein. And second, we send X-rays through it. The way X-rays are diffracted through the crystal gives us information on our protein. Now there is one issue. Unlike salt, proteins are not prone to crystallization, and therefore the whole process may take months when possible at all. Deciphering the structure of all proteins then became a key problem, and in 1994 a challenge was launched. The Critical Assessment of Protein Structure Prediction, CASP. Every 2 years the challenge was to find an algorithm to predict the shapes of the latest proteins uncovered before they are made public. The path to the Nobel Prize. Many participants tackled the challenge with many diverse approaches, and at the third CASP challenge in 1998, one algorithm stood out: Rosetta. The approach chosen by Rosetta's four conceptors, Simons, Bono, Rogzinski, and Baker, was very original. The CASP challenge was, given an amino acid sequence, to predict the shape of a protein. But what they did is an algorithm which, given a desired protein shape, computes the most likely amino acid sequence. That is, the inverse problem called protein design. At the 1998 CASP challenge, Rosetta's performance was among the best, yet still not accurate enough to reliably predict protein shapes. But where Rosetta truly shined is with its original purpose of protein design. In 2003, a group of 6 researchers, Kuhlmann, Dandas, Ayrton, Varani, Stoddard, and Baker, applied Rosetta to the design of a protein top 7. While it was not the first time that a protein was designed, top 7 came as a breakthrough for 3 reasons. First, it was a fairly long protein with its 93 amino acids. Now that's not long compared to some of the proteins found in the wild, but that's very long compared to most of the proteins that had been previously designed. Second, its shape was very different from any protein shape uncovered back then. And third, which is probably a byproduct of a second reason, its amino acid sequence did not have any significant similarity with any protein whose shape was already known. Those two works, the design of Rosetta to solve the 1998 CASP challenge and the application of Rosetta to design the protein top 7 in 2003, owed David Baker the 2024 Nobel Prize in Chemistry. That being said, the problem of protein shape prediction remained open, and until 2016, no algorithm ever achieved a score above 40% at any of the CASP challenges. That was until 2018 when a new participant entered the challenge, the company Google DeepMind, founded and led by Demis Hassabis. Google DeepMind's team, which included the aforementioned Demis Hassabis and John Jumper among many others, conceived algorithm AlphaFold and achieved a prediction score of 60%. That's way above the previously optimal score of 40% and also above the symbolic 50% threshold, making it a definitive breakthrough. But the story does not end here. At the next session of a CASP challenge in 2020, Google DeepMind did it again. An even larger team with John Jumper and Demis Hassabis on their front line achieved a staggering 90% prediction score with their improved algorithm AlphaFold 2. Such a high accuracy puts AlphaFold 2 almost on par with experimental methods like X-ray crystallography, and a year after, in 2021, they publicly released their predictions for all the 350,000 proteins that can be found in the human body. To put that in perspective, back in 2020, the number of human proteins whose shape was determined experimentally was right south of 2,000, representing an 18,000% increase. Based on all those results, the 2024 Nobel Prize in Chemistry is awarded for its one half to David Baker and for its other half jointly to Demis Hassabis and John Jumper, whose algorithm AlphaFold 2 led one of the founders of the CASP challenge to conclude the 2020 edition with the two words, "What now?" And indeed, what now? Well, as always in research, things are never completely over. First, as mentioned, AlphaFold 2 makes predictions based on experimental data. From that perspective, with their 90% accuracy, AlphaFold 2's predictions are a nice complementary resource to the world's protein data bank, whose experimental data remains the gold standard. Second, there are still proteins that AlphaFold 2 could not predict accurately, including highly dynamic proteins. That further explains why the CASP challenge is still ongoing, with a number of participants which has remained stable at around 100 over the recent years, still including Google DeepMind, who released the further improved algorithm AlphaFold 3 last year, 2024. Now for the rest of the video, we are going to see briefly how AlphaFold and AlphaFold 2 work. But before that, if you enjoyed this video, don't forget to give it a thumbs up and subscribe for more content like this one. AlphaFold and AlphaFold 2. First, AlphaFold. The algorithm's objective is to learn the 3D shape of the protein. For that purpose, AlphaFold will utilize two types of data: the sequences of amino acids, of course, but also the so-called multiple sequence alignments, or MSA, which captures similarities across different proteins. Say, for example, that you could collect one enzyme which has a specific function from several different species of animals. Then the similarities in the enzyme structure that appear across all species are likely to be a functional part of the enzyme. Those similarities are captured by the MSA. The learning process is in two steps. First, AlphaFold predicts the distances between the pairs of amino acids of the protein. And in the second step, using its distance predictions, it will learn the torsion angles by minimizing a potential function whose expression is partly inspired from Rosetta, Baker's algorithm, performed via gradient descent. Based on those torsion angles, AlphaFold can output the 3D shape of a protein. From an innovation perspective, AlphaFold was one of the first algorithms to learn the distances between the amino acid pairs. All such distances would be stored in a big matrix called histogram, which would be inferred by AlphaFold using the standard learning procedure for such a task, at least back in 2018, a deep convolutional neural network. Next comes AlphaFold 2. Its main difference from its predecessor is to replace the two-step learning process with a unified learning process composed of a series of 48 evoformer blocks. The evoformer, which integrates a 2017 neural architecture transformer, allows continuous interactions between the MSA and the amino acid pair representations, and hence enables direct reasoning about the spatial and evolutionary relationships. If you want to know more about this groundbreaking algorithm, I have put the link to the paper in the description box down below. Alright, that rounds out this video on the Nobel Prize in Chemistry 2024. Big congratulations to David Baker, Demis Hassabis and John Jumper for their formidable achievement and this more than well-deserved Nobel Prize in Chemistry 2024. As always, if you enjoyed this video, please give it a thumbs up, subscribe and hit the bell icon. I would really appreciate your support. Also, don't forget to check out my other videos for more or less technical content. Thanks again so much for watching. I wish you a wonderful week and I'll see you in the next video. Cheers.